Today I've got a really cool integral for you. So we're going to evaluate the integral from 0 to infinity of the natural log of x plus 1 over x all over x to the fourth plus 1. And we're going to start with one of the tricks that I really like. And that is to take half of this integral and add it to another half of this integral. So it may seem like, well, we're not really doing anything here. But what we'll do is perform a substitution on one of the halves, and then that'll give us something that can nicely recombine with the other half. So here, I'm just writing 2 copies of this integral. And then, like I said, let's do that substitution on, maybe it'll be the first half. So let's say this blue box over here will be the substitution that we're going to make. So what will it be? So I'm going to take x and set it equal to 1 over u. But let's observe that that means that dx is minus 1 over u squared. And then notice as x goes to 0 from above, that means that u is going to go to positive infinity. And then as x goes to positive infinity, that means that u is going to go to 0. So that's going to flip our bounds of integration to infinity to 0. But that being said, I'm going to take this minus sign here and have that flip the bounds of integration back. Okay, so let's see what that's going to leave us with real quick. So here we're going to have a half, and then an integral from 0 to infinity, and now we're going to have the natural log of 1 over u plus u. Because if we're replacing x with 1 over u, notice that x plus 1 over x is, well, it's going to be exactly the same thing. And then let's see, down here, we're going to have 1 over u to the fourth plus 1. And then we'll have 1 over u squared out front du, or I guess I should say in the back. And that comes from this dx component right here. I forgot my du. Okay. But now I'll just bring this second integral down. So I've got a half the integral from 0 to infinity of natural log of x plus 1 by x all over x to the fourth plus 1 dx. So something like that. Now what I'm going to do is multiply the numerator and the denominator of this first integral by u squared. So I'm going to put a u squared right here. But that's going to change this u squared to a u to the fourth. But now if I distribute this u to the fourth through to these two terms, that means that I've got a u to the fourth plus 1 again. But then I can make a dummy change of variables just from u back to x and recombine it with this right-hand integral, given that my denominators are the same. And then, well, let's maybe color code this a little bit. So here we made this substitution from here using this blue box substitution. And now I'm going to simply write this as 1/2, and then my integral from 0 to infinity of x squared plus 1 times the natural log of x plus 1 over x. And then this is all over x to the fourth plus 1 dx. Like I said, that's by that substitution that I just did, distributing this u to the fourth through, and then maybe swapping back u for x in the first one. Oh, and one last thing is, no, I still need my half here, so I cannot get rid of that half. So now what I'll do is divide the numerator and the denominator by x squared. That's going to put this into a slightly better form for us. So in fact, what is it going to look like? So we're going to have 1/2 and then the integral from 0 to infinity. So now this right here is going to look like 1 plus 1 over x squared. And then I have the natural log of x plus 1 over x. And then down here, I'm going to have x squared plus 1 over x squared, then dx out back. So now what I can do is complete the square in the denominator. So let's sketch out what that would look like over here in this orange box. So we can take this x squared plus 1 over x squared, and we can write it as x squared plus something plus 1 over x squared and then minus something. Then what is it going to take? Well, I think if we add 2 and we subtract 2, let's observe that this is going to factor like, well, we've really got a choice here. It's either x plus 1 over x or x minus 1 over x squared, depending on if we take our minus sign outside or inside of the parentheses. So let's perhaps put it inside the parentheses. And like I said, this is going to give us x minus 1 over x squared plus 2. Okay, nice. So let's bring that down here and write it up. So we've got all of our stuff just brought down. And then, like I said, this denominator is now x minus 1 over x quantity squared plus 2. Good. But now I'd like to observe the following. And that is, if I take u to be x minus 1 over x, then du is 1 plus 1 over x squared, just by taking the derivative using the power rule. So let's make that substitution here in this magenta box. So like I said, now we're going to make the substitution where u is x minus 1 over x. And then, let's see, like I said, du will be 1 plus 1 over x squared dx. So let's observe that this term right here, along with this, is our du. And then here I've got this u term. And then we'll sort out what this x plus 1 over x is in a minute, but let's see what happens. So as x approaches infinity, notice that u is going to be also approaching infinity. And then as x is approaching 0, let's observe that u is approaching minus infinity. So that's how the bounds of integration are going to change. And then for this x plus 1 over x inside of the natural log, we're going to do something kind of tricky. And that is, we're going to take this stuff inside of the natural log and square it. But then by logarithm rules, that's equivalent to dividing by 2 or multiplying by 2. So to undo it, we'll divide by 2. But we're going to do that because of this relationship that we have over here, which is x plus 1 over x squared is in fact simply u squared plus 4. So I'll let you guys check that, but that's exactly what that is. Okay, so now let's rewrite our integral in terms of our u's. So we've got minus infinity to infinity, like we said before. And then notice those are our du components. We have the natural log of u squared plus 4, like we discussed, over u squared plus 2 du. Okay, nice. And now what we'll do is use the fact that this is an even function to change this from an integral from minus infinity back to 0 to infinity. And so we can do that by multiplying by 2. So we've got a half and then the integral from 0 to infinity. And then while I'm at it, I'm going to change my variable of integration back to x. So I've got natural log of x squared plus 4 over x squared plus 2 dx. Now I'm going to do one of my favorite tricks, which is to view this as a double integral. Well, I'm going to first view it as the result of an inner integral that has been evaluated at some points, and then we're going to turn that into a double integral using the fundamental theorem of calculus. So let's observe that I can rewrite this as 1/2 and then the integral from 0 up to infinity of the natural log of x squared times y plus 4 all over x squared plus 2 evaluated from 0 to 1. So evaluating that at 1 clearly gives us the integral that we need, but then evaluating it at 0 gives us something that's non-zero. And since it's in the lower bound of integration, to undo that addition that we've caused, we need to add something on. So what we need to add on is the natural log of 4 over x squared plus 2. So we've got something like this at the moment. So just to be thorough, if we evaluate this at 0, we get minus natural log of 4 over x squared plus 2. So that's where that's going on. And then what I can do is use the fundamental theorem of calculus to take the derivative of this with respect to y, and that's going to change that to a double integral. And then simultaneously, I'll take the integral of natural log of 4 over x squared plus 2. But that x squared plus the square root of 2 squared has a standard antiderivative. So we're not going to write that down super carefully. We're just going to end up with something like this. So this is going to be 1/2, and then the integral from 0 to infinity, and then the integral from 0 to 1 of, let's see, it's going to be x squared over x squared plus 2 times x squared times y plus 4, and then dy dx. That's from taking the derivative of this with respect to y. And then on the outside here, we'll have plus pi times the natural log of 2 over 2 times the square root of 2. So you might say, well, where did that natural log of 4 go? Well, that really would have been natural log of 4 over 4 times the square root of 2, but then you were using logarithm rules to simplify it a little bit. Okay, cool. So now what are we going to do? Well, I think the next good step would be to take this stuff that I'm putting this box that's red around it and use a partial fraction decomposition with respect to the variable x. So just to kind of be thorough, what we're going to do, and I'm not going to do all the arithmetic, but we would write that as a over x squared plus 2, and then plus b over x squared times y plus 4. So if we can write it like that, we'd be good to go. And perhaps what we would really do is write it as ax plus b and cx plus d if you didn't want a and, let's see, our other b to depend on x. But what we'll see is those won't depend on x either. So in that setting over there, our b and d would be 0. So again, you set those two red boxes to each other, and then what you'll do is solve for a, b, c, and d in terms of y, because we're viewing x as our variable and y as a constant at this stage. All right, so now I'm going to take this pi times the natural log of 2 over 2 root 2 and bring it over to the left. And then I'll have plus 1/2, and then I'm going to switch my bounds of integration, or sorry, my order of integration. So I've got 0, 1, 0 to infinity, and then I'm doing that partial fraction decomposition that we discussed. And what you'll end up with is 1 over y minus 2, and then that's going to be multiplied into 1 over x squared plus 4 minus 1 over x squared y plus 4. And then let's see, we're going to have dx dy. And I think I said plus 4 here, but I meant plus 2. But now these inner integrals here are with respect to x, whereas this constant out here is with respect to y. So that's not going to have anything to do with those inner integrals. And those are inverse tangent integrals that I can evaluate at 0 and infinity, just keeping in mind that the limit as the argument of the inverse tangent approaches infinity is pi over 2. So those will give you those values. So what you'll get is the following. So let's maybe do this kind of all in one step. If we get rid of this integral right here, integrating this out, this bit turns into what? Well, it's going to turn into pi over 2 times the square root of 2 minus pi over 2 times the square root of y. So again, that's just from standard inverse tangent type integrations. And now what I'll do is I'll take this remaining y integral and I'll split it up across these two terms. So let's see. Bringing this down, that's going to give us pi times the natural log of 2 over 2 times the square root of 2. And then we'll have plus 1/2 our integral from 0 to 1 of 1 over y minus 2 dy. Oh, and I missed some terms here. That should be pi and then a 4 root 2 from the constant that's out there. And then I'll have minus pi over 4, and then the integral from 0 to 1 of 1 over the square root of y times y minus 2 dy. So we're left with something like that. Okay, so we're almost done, but we're running out of room, so let's start with a fresh board. Thanks for sticking around this long into the video. If you're enjoying what you see, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing, it really helps out. Okay, so this is where we left off on the last board. And before we do a step on the rest of this, I'd like to observe that this bit right here can be made a little bit simpler via substitution. So let's perhaps take y and set it equal to t squared. Notice that means that dy is going to be 2t dt. So let's see, if this right here, like I said, this 2y is 2t dt, notice that this term right here is also a t, which is going to cancel. And furthermore, it's going to cancel this 4 down to a 2. So now if I bring this down, I have pi natural log of 2 over 2 root 2 plus pi over 4 root 2 times the integral from 0 to 1 of dy over y minus 2. And then here I'm going to have minus pi over 2 now. The bounds of integration don't change. We have just 0 to 1 of dt over t squared plus 2. So we're left with something like that. And then, well, this integral over here can be done with a partial fraction decomposition. So in fact, what we can get is we can take this 1 over t squared minus 2, and we can write it as a over t minus the square root of 2 plus b over t plus the square root of 2. And just to maybe do this more thoroughly than we did the last one, let's explicitly calculate what a and b are. So notice that multiplying by the denominator t squared minus 2, we'll have 1 equals a times t plus root 2 plus b times t minus root 2. And then extracting the coefficient of, actually, let's maybe set t equal to the square root of 2, and that's going to give us what? That's going to give us 2 times the square root of 2 times a equals 1, which means that a is 1 over 2 root 2. And then likewise, we can quickly find that b is minus 1 over 2 root 2. And that's what those a's and b's are going to be. Okay, so let's bring some stuff down. So we've got that right there, and then plus pi over 4 root 2, and then that's going to be the natural log of the absolute value of y minus 2 evaluated from 0 to 1. And then let's get that second integral replaced with its partial fraction decomposition, but we'll like erase what we have there since we're running out of room in the horizontal. And there we have that. So now let's start our evaluation. So bringing this down, we have pi natural log of 2 over 2 root 2 plus, now evaluating this at 1 is going to give us natural log of 1, which is 0. Evaluating this at 0, we'll get natural log of 2, but that's attached to a minus sign given that it is in the lower bound of integration. So this is going to be minus pi natural log of 2 over 4 times the square root of 2 right there. And then let's see, for this next one, we'll have minus pi over 4 root 2. And then this is going to be the natural log of the absolute value of t plus the square root of 2 minus the natural log of t minus the square root of 2. So we could write that as t plus root 2 over t minus root 2. Using logarithm rules, and then we have to evaluate that from 0 to 1. Notice evaluating that at 0 will give us 0 because we'll get the natural log of 1. So evaluating that at 1 is the only kind of important piece of information. So let's see, these two terms are fairly similar, so we can put them together into a 2 log 2 over 2 root 2. And then we have minus pi over 4 root 2, and then that's going to be the log of, let's see, 1 plus root 2 over 1 minus root 2. And I guess that is a number. That would be the final solution, but there's some stuff you can do with logarithm rules and maybe multiplying by the radical conjugate in there that'll simplify it a little bit. And I'll just maybe go ahead and jump to the final number. And what you'll see is that this all simplifies down to pi over 4 times the square root of 2 times the natural log of 6 plus 4 times the square root of 2. And that's a good place to stop.